Oh, all right, guys. So how are we going to calculate this, Bojan? This is going to be straightforward because the condition that we want of this one is just the constructive, right? First minimum give you delta R equal to lambda over 2. That's it. Okay. So what is the delta R, Bojan? That is just R2 minus R1. And all you care about is just the difference. So I can put an absolute sign to it. Okay. And now I know that because R2 is going to be longer than R1, so it's going to be R2 minus R1. And R2 is just a distance from the speaker to point P. The R1 is the distance from the speaker 1 to point P. So that's it. All you need to do is just use the Pythagorean theorem for each of the R1 and R2 calculation. Okay, so that's not too bad. So you say R1 is just square root of 1.15 square right here and 8 square. Pythagorean theorem. That's R1. Same thing with R2. So R2 is just square root of 1.85 square plus 8 square. And once you got that number, plug it back into here, equate that to lambda over 2, you will be able to figure out lambda equal to what? Okay, not bad. And once you get the lambda, because they want to get the frequency, F equal to V over lambda that we just did in class. So if the value of the speed of sound is given like 350, you just plug in like 350 and then divided by the lambda that you just got here. There you go. And you are done. Not too bad. And for those of you that are confused, this is pretty much given. 350 meter per second, on and on. Depends on the information that you have. They might use 345, 340, doesn't matter. And that's how you get back to the frequency calculation. All right, guys. So I just want to emphasize that this interference calculation is simple. It's just Y1 plus Y2. That's a whole sort of like in the nutshell, that's it. It's a superposition principle. 1 plus 1 equal to 2 all the time. Okay. But just to make it like more, you know, like, okay, then is this it? Interference will give you only this, but no, there is another scenario that might be possible, guys. And this is an annoying part again, because it's just the algebra of the trigonometric function. Try this. Have you seen this before? First, let me ask you this one. Have you seen this diagram before in high school physics? Some of yes, some of you, maybe not a lot. Okay, just only maybe some. Okay, here we go. Here, what is this? All right. Well, what is this diagram? It turns out what you can do further with this is if I have something else to show you. Okay, you guys with me with this? Here, if I write it like this, guys, A sine kx minus omega t. Everyone okay? No problem. But then now I have another one. But then I have plus. Whoa. So that means right now I have two waves moving in the opposite direction. Give me the resultant wave right now. This is a quiz. maybe. Okay, just kidding. All right. What should be the resultant wave? Mà hãy ra nói. What should be the resultant wave from this? Just add them, right? No, it turns out, oh, it looks like a zero, but it's not. So what I'm going to do is this, guys, is simple because, all right, we know it's going to be just a simple addition of the two. And then what I can do is over here, I can pull out a common factor A. I have sine kx minus omega t plus sine kx plus omega t, right? And now I use the same identity. I can add the summation into a product. So I can turn this into 2 cosine, the difference over 2, and sine sum over 2, right? Same, using the same identity as before, okay? Do it, please. That's not bad. Okay, number 2 is in the front, A is there. Now let's do the cosine term. It's a difference over 2. Difference will cancel the kx, left which is the omega t. 2 of them divided by 2, 2 cancel. I have omega t left for the cosine term. Cool? You might be wondering, where is the negative sign? Don't worry, cosine negative or cosine positive give you the same numbers anyway. So I just only take the omega t. Sine, the sum over 2, just add them divided by 2. The omega t term cancel, you get 2kx, 2 cancel with the 2, you get kx at the end. Perfect. Haven't done anything new. It's just a superposition principle, y1 plus y2. But because right now you have an opposite traveling wave meet at one point, what do you see out of this? Do you see something here? This is cool. But then wait a second. You pretty much detached. You split the term of the time t and the position x. You're not seeing x and t together anymore. T is one, x is the other, right? And this is where the interesting things start to creep in, guys. Look at this. What do you see? T is time, x is position. T is time, x is position. T is time, x is position. See that? Let's see what happened when x equal to 0. What happened? Yeah, at x equal to 0, your total wave is gone. No matter when, no matter what time t. At x equal to 0, you get nothing. No matter when, no matter where. Right? I mean, here, where, sorry, no matter when. Yeah? Huh, no wave. But beyond that, if you change the value of x a little bit, okay, that's okay. You have a little bit there. But then once you hit, if the kx hit pi value, what you have? What happened there? Psi pi is also 0. Hey. So this means at x equal to pi over k, you hit another 0 points. No oscillation. Same thing with if I do kx equal to 2 pi, everyone knows sine of 2 pi will go to 0 again. Sine always hits 0 every time that the argument is a multiple of pi, right? Sine 0 is 0, sine pi is 0, sine 2 pi is 0, 3 pi, 4 pi, 5 pi, on and on. So from here, you can conclude, so that means at the position when kx equal to pi, but k, everyone know, is just 2 pi over lambda. So pi cancel, x equal to lambda over 2. Huh? And then I can just say about it's not only any pi, any multiple of pi will do the same thing. With me, guys? What do you see here? So what I'm saying over here is whenever the position is at 0, that's 0, when n equal to 0, or at lambda over 2, 2 lambda over 2, 3 lambda over 2, 4 lambda over 2, 5 lambda over 2, these positions will get nothing, no movement, because the resultant wave is 0 at any time. That's why we call this a standing wave. Here. This is the position that I'm talking about. Here. Here. There. 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 So these are the position where you always get 0 waves at all time. Okay? But everywhere else is still going crazy. But once you hit x equal to these conditions, bam, nothing, nothing, nothing. So when you look at it, it looks like it's a standing wave. It's like wave doesn't move because you have a fixed point that you can pretty much like pinpoint the wave down. But in reality, is two waves going in the opposite direction. Okay, but it looks to you just like wave just going, standing still. So that's why we call this a standing wave. Cool. All right. So that's the story of it. It looks complicated at first, but it's not, because it's just a simply application of the superposition principle. Where have you seen this? So look at this one, Wajan. So what are the difference between these three cases? Okay. So these three cases is just mean that it turns out there are many ways that you can fit the standing wave into this, let me call it a two, or a column, something that you can fit the wave in there and it will meet the standing wave condition. Kind of cool. All right. So you might not be able to understand what is so cool about it. All right. So this is what I'm going to show you together. Here we go. Look at this. This is a different scenario a little bit. In this slide, you have column that has two open ends. Both ends are open. Okay. But this one, Mojan, I have one end open, one end closed. That is another kind of movement that's going to happen inside. What kind of difference? Look at this one. Because it's guaranteed that the air molecule will not be able to move whatsoever at this wall. Okay, your molecule is against the wall, so it's guaranteed that that point the air cannot move, right? So it's a guarantee that this is going to be the point where you're not going to get any movement. So this is going to be the condition that, hey, I like this. I want the condition for that to be something we call node. A node are the places where you have no oscillation whatsoever. Okay. And this is the case. So I can say at the end of this, that's the node right there. Okay. And opposite to that, the place where the oscillation can still happen a lot, we call it the antinode. So that means whenever you want to create a standing wave inside an air column, it will be an alternation between antinode, node, antinode, node, antinode. However, whenever you meet the conditions, you always be able to generate standing wave. When I say meet the condition, what does it mean? It's this. Okay, let me do this together with you. So let me start from this. I hope this helps. First time seeing this is going to be confusing. I know it's kind of like, Ajahn, what is going on here? Here we go. If I have a tube that's one open, one end open, one end closed. The condition that I can put in is this is definitely going to be a node at the end of the tube. And the opening of the tube, I can put the antinode to it. So as long as I meet this criteria, I will be able to generate a standing wave. When I say, if I can meet the criteria, is this, guys? From the antinode to the node. So I draw this diagram right here. So this is sort of like the diagram that shows up. It's a diagram. It's not a real wave. It's a diagram just to identify the position where it's going to be a node, where it's going to be an antinode. Cool? But I can do one step better. As long as I keep the condition fixed, open end is an antinode, the closed end is a node, I can do one more flip. Bam, bam. That is still fine. I still meet the criteria. Opening end is antinode, the closed end is a node. This is also another possibility of standing wave. Okay? Or, Bajan, I can do one more better. I can do one more flip. Bam, 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 bam. That is still another standing wave. On and on and on. Cool? So that's it. So it seems like these problems of generating a node, an antinode, and a standing wave in the air column and everything, you don't need to really go back to this calculation anymore. This is what I just want to show you. That the standing wave can be created by having two waves that look exactly the same, moving in the opposite direction. Okay, once you do that, you have this going on here. Okay. But once you have, hey, Ajahn, the only way that you can only create this one is you just look at the position where you have no oscillation. Then that is the easiest place that you can place all the nodes in your system. And once you have that, You don't have to go back to this crazy additions of sine and cosine and all that stuff anymore. All you need to do is just rely on the diagram and try to meet the condition of the node and the antinode. อันนี้ทุกคนพอได้ไหมเก็ตไหม Yes. Opposite direction. Yeah, opposite direction. Inside, there must be something. And then, หมออาจารย์ where does it come from? Think of it this way. If I send in the sound wave, the sound wave will lift like that wall back. So that's when you have two waves going on. Sort of like going in the opposite direction all the time. Cool? All right. So this, we call it harmonic, guys. That's it. This is a sort of like more complicated setting for you to generate a sound. Because I said, if you have a simple setting, you're going to generate a single oscillation, a simple harmonic, you get a simple sound. But this one is not. Because you have multiple ways for you to meet the condition, then you're going to have a multiple frequency, and multiple frequency come to you right away. So there's a mixed, the wave sound would look complicated, okay? Where have you seen this before? It's right here. I have demonstration here. I don't know will that work or not. Let me try. Okay. I know. Wait. มันจะต้องกระจุยกระจายทำให้ไมค์อาจารย์เสียเนี่ยยังไม่ได้ใช้เนี่ย Okay, here we go, guys. So look at this. If you have this opening and the surface of the water, that is the closed end of it. Make sense? So what I have right now, if you look like upside down, it looks like this. There you go. Here. That's it. The water is down here. That's the water. So if I do this, I know. Okay. All right. So this is the opening end. This is the bottom end. And if you blow the top, you know that it's going to generate sound, right? Okay. Let me put that. Yeah. Okay. Let me do it. Okay. Is longer. It's lower. Right? You can keep doing this. Okay, anyway. But the point is, what you have over here is when you lower the surface level of water. So what you have here is, of course, you lower it down here. But the sound that you hear the most is going to be the one that can fit the condition that we just studied. So this is what you have here. Yeah, that. Okay, couple. So that's the condition that I can fit in, right? But of course, they're gonna be like a multiple clays over here. Of course, there'll be like a higher harmonic on and on. Okay, but the main sound that you hear will be the easiest harmonic that it can generate it. That will be the biggest harmonic sound that you will hear, which is going to be the fundamental, which is the first case, the first harmonic. That will be the loudest. All right. But if you have like a sound detector, look at the waveform of it, you will detect the next harmonic along with it as well. All right. But the loudest one is going to be the easiest one, the fundamental one, the first harmonic. But once you lower the level of the water, here, look at this. See that? Okay. But you already saw from our analysis, Ajahn, the distance between node and antinode, if you recognize this condition over here, Ajahn, the node will happen every half of wavelength, right? Every half of wavelength you have another node, and in a half of wavelength you have another node. So that means if you look at this one, the separation between node and the antinode will be half of the half. So it's going to be lambda over 4. Does that make sense? Okay. However, that means the lambda over 4 is going to be the length of the tube. So that means your lambda of the wave that fits the condition of generating the standing wave is 4 times the length. So back in here, the length of the tube is getting longer. So that's why your lambda is going to be 4 times of that. So you're going to get a longer wavelength when you lower the level of the water. That's why you hear the sound that have a lower tone. The pitch is going lower and lower. Think backward. This is the condition that you saw when you clean up, or I mean, you fill up a bottle of water. You turn on the water, fill up the bottle, it's like, see that? That the sound is higher pitch because you reduce the length of the air in that column.
Can you explain how lambda is going to go well?
Sure. Here, back here. So we said that the condition of this one is the left end is node. The right end has to be antinode, right? Over here. But back in the analysis of this superposition, we say the node happens every half a lambda. Every half a lambda, you get to the next node. Every half a lambda, you get to the next node. So the distance between nodes are half of a lambda. Okay, so back here. So distance of every node, no, this is half a lambda. This is half a lambda for every node. Okay, but the antinode is halfway of those all the time, right? Just like split in half. So you split the nodes distance into half. You get the distance between antinode and the node. So that's why for the fundamental, the first harmonic or the first case, that was the one, the distance between antinode and node is going to be lambda over 4. Cool. All right. So go back to the condition. Then when you fill up a bottle, you hear the pitch going higher. It's like, that's because you're reducing the length of the air column on the top part of the bottle. So your frequency going upward is opposite to this. All right. So that's what it is. All right. So that's what we can try to understand everything about the standing wave in the air column. All you need to do is just find the conditions and that's it. Draw a diagram like this. By having a known, think of it like a known condition of the distance between nodes equal to lambda over 2. That's it. Or A to N is lambda over 4. And you are pretty much good to go. Okay, you don't have to go back and doing the sign plus sign and use the identity anymore. Okay, so with this in mind, think of it this way, guys. Here, come back to this. So you understand how to deal with this. Open end tube is an open end tube. So this is good. So what you have here, Ajahn, is an open end. So it means both ends must be antinodes. That's gonna be the place where you that's the condition that you're gonna be able to generate a standing wave. And I have a demonstration here, guys. โอ้ใช้แบบของแถวนี้มากเลย so here we go. So the straw itself is that open end tube right here. So if you blow on it, that's what it is. That's when you have, that is the first harmonic that you hear. All right. If I cut this in half, which is not a cut. Once I do this, this is going to be one open, one closed. Okay. So if I do this, it's going to totally be different frequency. Okay. So I do it's open end. Okay. Something like that. And because, I mean, I suppose you have like a scissor over here. I can cut this while I'm blowing at it. And then you'll hear that the sound going higher pitch. Same thing with the water, same thing. Right? But the point is, I can meet that condition very easily on this open tube by saying that, Bochan, this is easy. All right, let me do this for you together. ง่ายไหมเรื่องนี้สนุกดีนะ แต่จะบอกว่าเป็น demonstration ที่อุบาท looking มาก I'm saying you คือมันควรจะ have a better demonstrating, you know, devices or this. Okay, so the condition here, อาจารย์ for open end tubes, it's going to be antinode to antinode. The easiest that you can do is going like this. Aจารย์, this is easy. Yeah, that's going to be the easiest kind. So this, I'm going to call this a fundamental, or is the first harmonic. Okay, all right, so that's what it is. but then อาจารย์ I can do one step better if I want to. I can do one more flip, like that. That will be fine too because I started from antinode all the way to another antinode. And อาจารย์ I can do one more better by do another flip. On and on. So you can do this, bam, 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 like that. Okay, and now your analysis is going to go very simply by saying about that. I know the distance from antinode to antinode must be lambda over 2, right? All the time. So all you can do is just, this case, lambda over 2 is the length of the 2. But if I want to do one more twist, but no problem. That's a node, that's a node. So that's an antinode, halfway is antinode, that's another antinode. So it's 2 of the lambda over 2. So in this case, lambda is the length of the 2. And all you have to do is just counting the distance, pretty much. Like, that's an antinode, node, that's an antinode, 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 antinode. So it's going to be 3 lambda over 2 equal to the length of the tube, on and on and on. Okay, so what you can do is, because they are all different in wavelength, you can put a subscript to identify this. I can call this a fundamental frequency. I call this the lambda 1. Okay, that's the first harmonic that you can generate from this open tube. And then, if I want, usually when you talk about harmonic, you talk about frequency, not the wavelength. But no problem. Frequency is V over lambda. So the first harmonic is just going to be V over the first wavelength that you can fit in there. And then I put V equal to, here, move 2 to the right is 2L. That's it, guys. That is your fundamental frequency, V over 2L. And if I do this for the second case, frequency is V over lambda. It's going to be V over L. And I can just plug in number 2 over 2. Okay, wait for me a little bit here, guys. This is just the notation here. But V over 2L is just your fundamental. So that means your next standing wave that you can create is twice the frequency of the fundamental. With me? So we're going to call this second harmonic. So I put a subscript 2 in it. So this is your second harmonic. Cool. All right. And now your life goes on, but I can start to see the pattern here. The frequency of this one is going to be V over lambda, and it's going to be V over 2L with the number 3 on top. Okay. And once again, I say V over 2L is my fundamental. So I can say this is going to be 3 times my fundamental. So I'm going to call this third harmonic. There you go. On and on and on. That's how I sort of like set up the terminology, how to call these harmonics. Like this one is twice the fundamental. So this is your second harmonic. Okay, this of the fundamental, you call it the, okay. So I'm just saying that how many times the frequency relative to the fundamental frequency. With me? Cool. All right. That's what it is. And with that, Bajan, why do we care so much about this? Because we need to communicate. So if you look carefully with this, Bajan, for this, okay, we have fundamental to be V over lambda, and it's going to be V over 4L. So last question of the day, guys. What should be the next harmonic for this one open, one closed? มาคำถามสุดท้ายจะได้ไม่เครียด บอกอาจารย์ that's not hard because when you look at this one, this is lambda over 4 and lambda over 2. So for this case, you're gonna have, okay, let me move this away a little bit.มีปัญหาทำไมอาจารย์ไม่ใช้ iPad ใช่รอสักวันสักวันนักศึกษาจะสปอนเซอร์ iPad อาจารย์ คืออาจารย์ทำให้มันดูเหมือนชีวิตลำบากไงจนถึงว่าอาจารย์เดี๋ยวผมซื้อให้มา Okay, so here we go. For the second case, you see that the whole length of the tube is going to be 3 lambda over 4, right? Equal to L. So that means the lambda is 4L over 3. So that means your frequency for this case is going to be V over lambda. And it's going to be V over 4L, but with the number 3 on top. When you have the number 3 on top, บอกอาจารย์ wait. That is triple the fundamental. See that? Yeah. So the next harmonic for the open, one closed tube is 3 times the fundamental. So we have to call this the third harmonic. Get yang. That's the way to name it. That's your first harmonic. There you go, guys. That's done. Now, so all you have to worry about is just you know the distance between node to node or anti-node to node. That's all you have. The rest, just make it to fit with the condition that you have for your system. Is it one open, one closed, or 2 sides open? And then you just set up the correct distance between node and anti-node. You will be able to figuring out the frequency. All right. So if you're still confused, don't worry. Next time we'll do this one more time. All right. And I will show you a better simulation than just my demonstration. I think, yeah, a better simulation might help. All right. But anyway, the point is I'm gonna have to call the next harmonic the third harmonic for the open, one closed tube. All right, guys. Thank you for sticking around. I'll see you guys on Monday on site. And so sorry about the previous Monday, I mean 2 days ago. Totally thought it's a holiday.